Here we're showing a programmable thermostat along with an old humidistat on there. I still run into these old programmables, but nowadays everybody seems to be going with the Nest or, like I said, the Ecobees, and there's a few other ones where they're dialed, and they're different. New technology is always going to come out. Um, the biggest thing that I got, and it sounds dumb, all right, but every time I change a thermostat in somebody's house, I always want to remember where that thing was set at, and I want to change it back to where I found it. Um, my whole goal is not to upset the person who's still living there. We've already done quite a bit of violating of their privacy. We're going into their home and we're giving it a thorough once over. And me included, it's kind of an uneasy feeling when somebody else is in there judging you and every part of your home that's on there. And it's easy to upset people with this. They're used to certain temperatures in their home and they want to have those certain temperatures. If I come in there and I raise it up to 80 degrees and all of a sudden they come home to a house that's 80 degrees, they're not going to be happy with me. The good news is that if they don't come home for a little while, these programmable thermostats still usually go back to their programming. So you don't override them permanently. You just override them till the next setting comes around. But either way, it's just good practice to return that thing back to where you found it. Right. Shut-off switches, like I said, they should be in the same room wherever the furnace is. I kind of like them mounted on the furnace myself. It kind of verifies that the furnace is also grounded when it's connected to our conduit system and our junction box and so forth that's on there. To me, it's just a smart way to protect it. All right, we're going to start getting into our different types of furnaces. The first one you're expected to recognize is called a gravity furnace. Gravity furnaces did nothing but turn a fire on and turn a fire off. The heat exchangers of these things were thick cast iron. I want to say probably about 1.5 inches to 2 inches thick, maybe even 3 inches. They were just big and solid, all right? The fire would burn, heat up. It would get that cast iron refractory pot super hot. The circulation air would be on the outside. And as I mentioned earlier, we don't have a blower fan on these, so it worked on the principle of convection with hot air normally rising. So the hot air would start to rise. We would have our registers, our grills, our diffusers, whatever we had, they would be in the middle of the home. So the hot air would have the shortest, straightest distance going up, and then that would start dumping into the rooms. Usually I would have one central return that comes back down on these things, and they're old. I don't know what much more to say. These are typically going to be in houses that were built before World War II. I don't think we were really using these things after World War II, but there is a possibility. But most of them are going to be in homes before World War II. No blower fans, no filters, slow air movement. Principle that hot air rises, cold air falls, creating a convection loop. So the hot air would come up here, and we'll leave through this room here, and then cold air would come back down, get reheated, and basically we're creating a convection loop inside here for a gravity furnace. This is a typical gravity furnace that comes in here. As far as test questions that you might get on a state exam or on a one final, it's kind of the duct sizes that I want you to be aware of. Let me go to the next one. I think that might help. So the returns. So this is a return. Back here is a return. These things are supposed to be 3 times as big as whatever the supplies are. So these are our supplies. Typically these are going to be 8-inch ducts that go to the different rooms, and these would be 2-foot returns that come back. Again, no filter, no fan, or nothing else. Over here is going to be my vent connector. And if I follow that, that's going to go to the chimney. We go back to the front of this. If I open up this door right here, I can literally stick my head inside that heat exchanger, all right, and look at the entire inside of it. It will be smaller than what we're looking at here. There is going to be an airspace that runs between the outside jacket and the inside refractory pot. And as that gets hot, again, that's going to create that hot air movement. Hot air naturally wants to rise. And they work. Because these heat exchangers are so old and so thick, chances are good that there's not going to be a crack or a hole in that heat exchanger at all. It's going to be intact, and there's not going to be a good reason that you're going to tell someone to replace it, other than you want to go ahead and increase the efficiency. But the biggest thing with these things is because, as I mentioned, old school, we put the discharges or the supply registers in the middle of the house. Well, new school, we put those on the outside walls, so the outside of the house. And the reason is, and usually by windows and doors, those are going to be our areas where we had the most amount of heat loss. So we're going to want to replace the heat at those locations before we go anywhere else. And then here we're going to have one central return. So usually switching these things out, people do try to put a forced air furnace and use the same ductwork. But for the most part, you're probably going to end up putting new ductwork in there as well. Gravity furnace. Now, I know it says Octopus on there, and that's more of a nickname than anything else. And if you look at the ductwork coming out of the top of this one, the actual piece itself kind of looks like the body of a squid and all the legs that are coming off of it. But the real name I want you to know is gravity furnace. No blower fan, nothing but turn fire on, turn it off. No filter. There's nothing to go ahead and get the circulation in. All right. So here we're going to switch over to forced air furnaces. And this is actually a oil furnace. So anytime I get that blow dryer looking object in any diagram, that's pretty much an oil burner that we're looking at. And if I come up here to the right side, right above the dot there, you can see that's our barometric damper that we talked about earlier. All right. Now, airflow into forced air furnaces is important. All right. And it should always be the same way. Now, they're showing this where it almost looks like the vent or the vent connector is going through the return air. Yeah, there was a very short time frame where that happened, but we don't do that anymore. Pressure differentials are very important in the safety of how these heating units work. All right. So first thing we want to do is talk about the airflow. So the return air comes in. The first thing we're going to do is filter that air. All right. After we filter that air, then we're going to pressurize that air. So right now, here's our blower fan. So filter, fan, then we're going to go to our heat exchanger. And then last but not least, if I had an air conditioning system, and this one doesn't show it, if I had an air conditioning system, the air conditioning system would be last. So filter, fan, heat exchanger, air conditioning system. Now, if I had the fan running down here, that fan on this side of the fan, the filter side, is going to be under a negative pressure. After the fan, it's going to be under a positive pressure. If I ran this pipe through the negative pressure and I had a hole or a crack or something where we saw that rust corroding it, I'm actually going to be creating a vacuum and pulling the bad gases and the carbon monoxide into my circulation air. So we don't want to have any sort of venting running through a low pressure zone like any ductwork that's going to be before my blower fan. All right. And then if we think about it, even if I had a hole in my heat exchanger, because now if this is under zero pressure, because I do not have an inducer fan, if I had an inducer fan, I would create a negative pressure inside here. And then I would also have a positive pressure being created on the outside of the heat exchanger. If I did have a hole or crack or opening in there, that means that the air would be flowing into the heat exchanger instead of allowing gases to escape. Please don't take what I just said as me saying that it's okay to have a hole or a crack in the heat exchanger. It is not, by any means. All I'm saying is the design of these furnaces, we have multiple different safety features that are put into these things. So the first one is going to be our fuel air mixture. If that oil burner is doing what it's supposed to be doing, or my gas burners or propane burners are tuned right, I'm going to produce very low levels of carbon monoxide. The carbon monoxide is what's going to harm a human being. All right, so that's safety feature number one. The heat exchanger itself, if that's intact and there's no cracks, openings, or anything else in there, then there's no way for those bad gases to pass over and get into my circulation air. Safety feature number two. And then the third one is going to be my air pressure differentials. I have to have my blower fan before that heat exchanger because I want to create a positive pressure on the outside of that heat exchanger so that if I did have any openings, I'm going to lower or reduce the risk of carbon monoxide getting into my circulation air and then hence coming into my house. All right. So new school, we put our radiators under the windows and we bring our return air from the outside. And then you'll see on just about every other slide that we show for forced air furnaces, it's going to be filter fan, heat exchanger, air conditioner. All right. Airflow and ductworks. This is another complaint call. If you don't take the time to check, you will run into houses that A, don't even have a heat source in a room. We've run into that a few times. B, they're going to be at very odd locations, like right in the middle of the ceiling someplace, and it was added afterwards. Or you just get a real cruddy flow coming out of it. So our shortcut method is to take the thermal imager around and we shine it on all the openings where the exhausts are coming out of there, and the furnace was running for about 5-10 minutes already. I would not only want to see that the grill itself is warm, but if it's close to the wall, I actually like to see flame patterns on the wall so that I know heat is hitting that and it's coming out of there. All right. Same thing for the ceilings and so forth. If I see just warm air, I typically go over the area and I just use my sock. I take my shoes off in most homes. Otherwise, I use the back of my hand. I think it's called an anemometer, which checks for airflow. I know some people will put that on there. There's nothing wrong with it. I think I'm a big fan about more data, more definitive answers when we do our test. So if I want to say that I have slow airflow coming out of one ductwork, and I could show that I have 40 cubic feet from this one, 35 from that one, 41 from this one, 38 from this one, and 4 from this one here, and I could show numbers on each one of them, I think that really sends the message home that I have low airflow coming out of this one for my clients in case they want to negotiate these things. So the shapes, the more round they are, the easier air is to flow. The distance and size of the ductwork matters. The smoothness inside. We find those corrugated loop ones sometimes in attics. It's not very common in the Chicago area, but it's getting to be more and more common. So the rougher they are, the bigger the chance to reduce the airflow, the bigger the pipes that they need to be. Hot air does move easier through ductwork than cold air. So not only do we have to size the ductwork for the heat, but we also have to size it for the air conditioning. Typically, most furnace fans, they're going to blow at a higher speed when it's running in air conditioning mode because we know cold air is harder to push through the ductwork. So the fan will make up that weakness that it needs. All right. And obviously, keeping a furnace in the middle is always going to be the best thing we can do. I would like you to be able to recognize the difference between a register, a grill, and a diffuser. All right. So a register is going to have a damper on it. Typically, we'll find these in the floors and the walls, and also in the ceilings. Grills are basically the same thing as a damper, but there's not. I'm sorry, they're the same thing as a register, but there is no damper on them. All right. Where diffusers, it has different angles, so basically it kind of spreads the air out more throughout the room. Typically, we're going to find those in ceilings. We really don't find them in floors and walls. But yeah, up in the attic spots, you're going to find diffusers. Registers, they have dampers. Grills do not. Diffusers are going to be typically in the ceiling. Registers are typically going to be on supplies. Grills are going to be typically on returns. And diffusers are going to be typically on supplies. So when we're blowing air into a room, sometimes we're going to run into ductwork or return ducts where there'll be a register and a grill. So typically they'll have a grill on top and a register on the bottom. To use these things to the fullest advantage, we want to realize what we're trying to do to the room and remove what we're not trying to do to the room, if that makes sense. So in other words, they're showing the top drawing being in cooling mode, so in the summer. So the air conditioning is running, all right? So if I want to add cool air to the room, that means I want to remove hot air from the room. So the hot air is always going to be higher, so I want to remove air from the top. So the bottom register, I'm going to close that register, close that damper. And that way air won't flow in through there, and it's going to pull all the air from the top where it's warm. And we're going to pull that down to get reconditioned. The bottom illustration in the winter mode, what they did is they opened up that damper that blocks the grill above it. And so we're going to be pulling in the cool air. Cool air is found down low. We'll be pulling that into the house. Not all homes have this, but if you do happen to do an inspection on a house that does have this, you should be able to explain to your client why it's there, how to work it, and how to make it the most efficient. So as we're showing on this drawing here, the grill is on top, the register is on the bottom. When it's in heat mode or the furnace is running heat, we want that register on the bottom open, so the damper open. And when we're running in air conditioning mode, we want to take it from the top, so we close the damper. We're going to run into houses also that have a central return still. Most of the time, that's where we're going to find our filter when we do have that central return. So we want to show our clients how to open it and change it. If they know already, that's great. If they don't, they're going to want to learn. All right. We also need to make sure that the air can flow in and out of that room with ease. All right. Not only when the door is open, but when the door is closed. So these things are designed to be where there's an undercut, I guess, under that door, so that as I'm blowing air in, I can let the air get out. If I have carpeting or that opening's too small, that's going to restrict the amount of airflow that's coming out of there. I've seen where they'll put grills up in the ceiling as well. I think that's a great idea, something that permanently lets it get out of there. One test that I do, and very rarely, but I have found them, where these things are problems, I make sure all the bedroom doors are closed inside, and I'll go into each bedroom door and I'll open it with the furnace running or the air conditioning running, just as long as there's airflow coming through there. And then I'm going to push that door closed, and I'm going to push it slowly closed. And if I get towards the end and it pulls away and kind of slams shut, that's a no-brainer. I mean, something's restricting the airflow out of there. It wants to flow, and we need to let it flow, all right? And so either we undercut the door more, or we have to put in another vent or something in order to let that air get through there. Again, our filters, I can't stress enough to my clients the importance of keeping these air filters clean, keeping them changed. People always ask, how often should we do it? And to me, it depends on the filter. I know they have some of them that you could keep in there for a year, and they have other ones that you should be changing every 30 days. All right. I think it matters more so how much air you're flowing, how clean your house is, pets. There's a lot of other things that come into play. But the main purpose of these filters is to filter the air. But when they get dirty, they also restrict the airflow that comes across. One of the numbers or one of the measurements I'm hoping you're going to be taking in your system is what we call the delta T, or the temperature change going across the heat exchanger. So it's what they refer to as the temperature rise. We'll find that number on the data plates inside the furnaces. Typically, they're going to be a 30-degree range, all right? And I've seen them anywhere from 25 to 55, all the way up to 55 to 85 degrees, all right? And I'm sure it would be even more than that, but those are pretty much the ranges that I see. So what that means is if I got a 70-degree temperature in the house and I got a 30 to 60 temperature rise, that means I should be between 100 and 130 degrees. So I'm going to take one of those dial thermometers or turkey thermometers or whatever other device I have. I'm going to measure either the air where the filter is, which is pretty much the room air, and you could see that on your thermostat. And then I'm going to go above the plenum and measure that temperature there as well. And if I'm too high, I like to remove the filter and see if that lowers that temperature back down to normal. Because if that filter is restricting the airflow and now my circulation air is slowed down coming across that, it's going to absorb a lot more heat. And that actually shortens the lifespan of these furnaces, because those metals in that heat exchanger, everything, when it gets hot, it expands. When it gets cold, it shrinks. And they're only designed to work on a certain temperature rise, all right? If I start overheating them or overcooling them, then that shortens their lifespan. We don't want to leave it like that. So making sure we're within that range is kind of a big deal to me. All right. Here they ran some ductwork through the garage, and they actually have a diffuser up in the ceiling of the garage. Sounds great. Now I got a heated garage, so everything's good. But we're going to talk about this, if I do an exterior one, which I think I will. We're going to end up talking about breaching of the firewall. So if I have an opening with ductwork that comes back into the house, if there's any gas fumes that's coming from the garage, or God forbid there's a fire, that just makes it an easy way coming in there. Same thing with the ductwork. Now I can run ductwork through a garage. That's not a problem. But it does have to be in a soffit. It does have to be protected by drywall. Just being out in the open isn't a good idea. There was a time frame when that wasn't considered a problem. In houses that were built after World War II, they used that garage space to get heat to different rooms. But I don't know when it changed and all. But in today's day, new construction, and even if I saw that, I would still say it's not a good idea, and I would do what I can to encourage somebody to get some sort of drywall or something wrapped around it at all, just to make it a little more airtight. All right. Older blower fans, belt-driven ones, I would encourage my client to get a belt and leave it on the ground there. Those things break at the worst times. But again, if I start seeing these older things nowadays, I would have to warn my client that this is just an older unit and it will fail eventually, and they're going to be getting an upgrade as that comes along. Everything now, these blower fans, they're all direct drive, so the motors are actually built into the fan, so we don't use belts anymore where it comes to it. And they're also multi-speed ones, or adjustable speeds. So you can actually program them on the computer by how much air it forces through the ductwork. And as I said earlier, cold air, harder to push, more fan speed. These belt-driven ones, they were one speed only. So when we start getting into our forced air furnaces now, we need to start learning the different parts that we're going to be finding inside the furnace. All right. I talk about the temperature rise that we measure with those turkey thermometers or little dial thermometers, and this area up here the ductwork that would be there, that would be called the plenum. And this is the area that I usually take that measurement. So when I'm talking about a 30 to 60 degree temperature rise, if we come in here at 70, this is where my heat exchanger is going to be. That's where I'm going to add heat to it. And then above the heat exchanger and my plenum, that's where I want to be at that 100 to 130 degree mark. All right. Now, if this blower fan fails, and because that fire is going to be lit, that fire is going to be constantly adding BTUs to the metal of the heat exchanger. So it's going to keep getting hotter and hotter and hotter. This furnace is engineered that as many BTUs as I'm adding through the fire here, I'm going to be removing those BTUs with the blower fan that I'm circulating air through the house. All right. So if that blower fan fails, whether the motor seizes up, comes loose, something blocks it, the wires come disconnected, whatever, I'm not able to remove the BTUs. So this furnace is going to get hotter and hotter and hotter. That's what this high limit switch or fan switch does. All right. Older units, this was a dial type machine on here, and it would have that same coil that we saw with the thermostats on there. And this is actually what turned the fan on and off back in the day. All right. So when the furnace would kick on, the burners would ignite and they would start heating up the heat exchanger, and the fan wouldn't kick on right away because the air around the heat exchanger is still cold. And we don't want to circulate cold air. We want to wait till it gets warm. So that would wait till somewhere around like 140 degrees. All right. At 140 degrees, this probe would flip a switch and say, okay, blower fan, you get turned on. All right. But again, let's say that blower fan was broken and it didn't operate. Then it would keep getting hotter and hotter and hotter until it reached somewhere around 170, 180 degrees. At that point in time, it's too hot, and that would actually turn the fire off and shut down the whole furnace and let everything cool back down again so that it didn't burn the house down, or start on fire itself. But let's say it was working, the blower fan was removing the heat, I'm staying within that safety zone, I didn't reach the high limit on there, then what happens is my thermostat is satisfied. The thermostat says, okay, it's enough, you can shut down. We may mention before that the heat exchanger is still hot, even though the fire is not there anymore, so we're still going to use that air. Using that air basically is what this fan limit switch does. So it's going to let that fan run until it gets down to somewhere around 100 degrees, plus or minus. And then once it gets there, it knows that there's no more usable heat, and then it shuts the blower fan off. All right. Sorry about that. Okay. So fan on, 140. Fan off, 100. Furnace shutdown, 200 is a nice, easy number to remember. All right. You can adjust that. All right. And I've never run into this where this thing was set off that much. I do pull that cover off. I do check those numbers if I see an old furnace like this, just to make sure it's not there. But if somebody has this thing set up to 350 degrees just to keep that thing going, that's not a good thing. All right. They can go, they're really turning it into a gravity furnace, but the amount of heat that's there is not going to be a positive thing. So there's an actual picture of what it looks like, and that's what is circled right in here. Typically, it's going to be between two of the heat exchangers. So if I go down on the bottom, that's where the burners are. That has its own heat exchanger coming up here. That's another heat exchanger and another heat exchanger and so forth. The air is going to flow between the two heat exchangers, and that's where we're going to find this temperature sensor that's going to be in the circulation air, the air that we breathe. All right.